Very good afternoon to all the esteemed gathering here for the second day of the second week of teacher enrichment workshop entitled as Differential Equations and Mathematical Modeling in collaboration with National Center for Mathematics, a joint center of IIT Bombay and TIFR Mumbai. First and foremost, I would like to request all the participants to please keep your mic at the mute mode so that we can have the smooth functioning of the session. So now, in continuation of our previous sessions, today we are going to start with our expert lecture by Professor Rashmi Bhardwaj ma'am. It's our proud privilege that Professor Rashmi Bhardwaj ma'am is an integral part of this TEW, and we are really grateful to ma'am for providing your precious time for this TEW and investing her sincere efforts for all the participants of this workshop. Professor Rashmi Bhardwaj ma'am is currently working as a professor in the Department of Mathematics and head of Nonlinear Dynamic Research Lab, University School of Basic and Applied Sciences, GGSIPU, Delhi. She has obtained her PhD in mathematics from University of Delhi. Prior to her doctorate, she has been a topper of Zakir Hussain College, DU, in BSc and MSc examinations. In fact, she was the second topper of University of Delhi in MSc examination. She has, to her credit, more than 25 years of teaching and around 30 years of research experience. She has supervised 13 candidates for PhD degree and 6 are currently working under her supervision. She has published more than 200 research papers in journals of national and international repute and conferences. Also, she has published 2 books and edited 1 proceedings of international conference. She is a subject reviewer for many international journals of high repute and lifetime member of several international organizations in the sphere of mathematical sciences, including Indian National Science Congress. She has attended and delivered talks and chaired various technical sessions at reputed academic conferences and workshops across the world. Her area of specialization include dynamical astronomy, nonlinear dynamics, applied and computational mathematics, statistics, wavelet, fractals, complex dynamics, ordinary and partial differential equation, numerical analysis, fluid dynamics and optimization, microfluidic, nanofluidic, atmospheric and environmental sciences, fuzzy mathematics, optimization techniques, soft computing, data science, machine learning, integral equation and boundary value problems, financial mathematics, and many more are there. She is also the recipient of various awards and fellowships like GGSIPU Best Researcher Award for 3 consecutive years, AICTE Young Scientist Award, University Grant Commission Major Research Project are few to name here, but the list is very long. Moreover, she is visiting associate of Inter-University Center for Astronomy and Astrophysics, Pune, India, and member of Sectional Committee of Section of Mathematical Sciences, including Statistics. And she is a member of Sectional Committee of Section of Mathematical Sciences, along with Indian Mathematical Science Congress Association, professional body under Department of Science and Technology, Ministry of Science and Technology, Government of India, and Government of India, Ministry of Earth Sciences has awarded ma'am 27th Biennial Museum Award with the cash prize and citation with co-authors on IMD Day, January 15, 2016. So this list is actually very long, but these are the few ones. So we are really privileged that ma'am is here for delivering the lecture to all the participants for this workshop. So with these words, I would like to request Professor Rashmi Bhardwaj ma'am to please start the session.
Yeah, thank you. Thank you to JP Institute. I think I'm a constant member or for all the workshops. Anyway, I feel privileged to be a part of that group.
Thank you, ma'am.
Thank you, ma'am.
Yeah, thank you very much.
Actually, we are learning a lot of things from you now because you just made a significant contribution for
No,
the
no.
mathematicians.
Actually, recently I got a NBHM project 2 days earlier.
Good.
Yeah, so
Congratulations, ma'am.
thank you. Now I will try to keep the presentation so simple for the first part, ki what is nonlinear dynamics. And for the second part, I will take some tools for the nonlinear dynamics. So I will try to keep as simple as it will be understandable to everyone. Let's see what I can make a simple way for presenting it. Is it visible?
Yes, ma'am, perfectly fine.
Yes, it is visible.
So I took a simple as a nonlinear dynamics. You see, it is nothing but a wave, how it changes its orientation. So firstly, before started, actually, I just give us something that what is a dynamical system and how we differentiate them with a linear or nonlinear system. So everyone, we know that dynamical system is a system that changes over time according to a set fixed rules that determine how one state of the system moves to the another system. So it is basically a phase space together with the transformation of that space. So it has two parts. One is a state vector, another one is a function. A state vector is one which describes exactly the state of some real or hypothetical systems like this, which is x bar t equal to x1t, x2t, or xnt. So it is nothing but a different states. And when we are coming to the function, which tells us that given the current state, what the state of the system in the next instant of time. So you have two types of the form. One is a state vector, another one is a function form. So state vector is simply a position vector at any time, which is depending on the different vectors of that. And when we are talking about the function, it will be defined as a single function or a set of functions which are depending on all these points. So f1 is at particular point, which is depending on all these state vectors, f2 and like fn. So now if we have to check that what is the condition or how we have to operate it. So in general, if we have a set of differential equations or equation of motions like dx1 by dt, which we denote normally x1 dot is equal to function of at one state, dx2 by dt equal to x2 dot, which is a f2 function, and like this dxn by dt equal to xn dot, which is a fn of x1, x2, xn. Now our purpose is to that when we are transforming any system into the equation forms, so now our purpose is to solve only a differential equation, and that with that differential equation we have to finalize which kind of the behavior of the system is. So if we have to transform the systems, there are majorly these type of the dynamical system, linear or non-linear. If we say in general, the category is either the system is a linear or a non-linear. If it is a linear, then it is an autonomous system. If it is non-linear, then it is a non-autonomous system. Linear systems are normally conservative in nature, and nonlinear is non-conservative systems. Linear is mostly the discrete system because we are taking it as at a point, particular point. And nonlinear is a continuous system. Linear is a one-dimensional, and once we are talking about the nonlinear, it is a multi-dimensional systems. So now when we are talking about the linear system, so these are the systems that have a certain set of properties. So what we have, suppose any input system or signal is going to the system, and then whatever be the output you are getting it is depend on the what kind of the function you are selecting inside of the that system. So when we have the linear system, Normally, we have that it satisfies the two type of the properties. One is the additive property and the another one is a homogeneity property. So what is the additive property? Suppose y is the function of x and u. So additive means you are taking only on the first system, f of a1 x1 plus f of a2 means a2 x2 of u is nothing but a1 of fx1 u plus a2 of fx2u. Same way if you have on the another part, same property a1 of fxu1 plus a2 of fx2. So this is giving you that the regularity of the system. So basically linear system is a function which describing the system behavior which must satisfy additivity, which is f of x plus y is nothing but fx plus fy, and the homogeneity of the function which shows that f of ax equal to a of fx. So suppose I am taking a simple example. Let fx is 3x, fy is 3y. If I am adding f of x plus y, so f of x plus y is nothing but 3 of x plus y. And if I am solving it, it is nothing but 3x plus 3y, which is equal to fx plus fy. And if we are coming to the homogeneity of the system, suppose I have to take f of 5x. So that is equal to 5x, which is, 5 into 3x, which is nothing but 15x, which is equal to f of 5x. So this means both the properties, additivity as well as homogeneity, is satisfied for this function. So that's why this function is an example of a linear system. Now, if I am coming to the nonlinear system, that is a system which is described by a nonlinear function and it does not satisfy these two properties. Suppose I am taking simple example, fx equal to x square. So of course fy is y square. Now if I have to find out f of x plus y, so f of x plus y is nothing but it is x plus y whole square, which comes to be x square plus 2xy plus y square. Now this term is extra. So it is not equal to fx plus fy, which is x square plus y square. So this means this function x square is not a linear function. It is a nonlinear function. And again, if you are satisfying the other property as a homogeneity, f of 5x is 5x whole square, which comes to be 25x square, which is not equal to 5 of fx. So it is not satisfying any of the property. That's why it is a nonlinear system. So what is tricky about the nonlinear system? Basically, we cannot say that it has or it is satisfying any solution. So you don't have a bounded solution in this case. Like if we have the dx by dt equal to minus of signum function at the initial condition as 0, or we have the example of 3x to power 2 by 3 when x equal to 0, or x square. So these are the type of the nonlinear systems which required some tricky solutions or some tricky way to find out the solutions of these functions. Now we come to the autonomous and non-autonomous system. If we have a time invariant system, these are called the autonomous system, which are not depending on the time. But if it is time depending or time varying, then it is a non-autonomous system. So in autonomous system, suppose we have the example of x dot equal to ax. So when you are taking the function, which is y equal to y dot equal to cx, then y equal to function of x only, not a depending on the time. Thus, autonomous are time invariant system with no external input, and will address only the nonlinear system, both time invariant and time varying. But mostly autonomous systems are having only the time invariant systems. So autonomous is a system of ordinary differential equations which do not depend on the independent variable. If the independent variable is time, we call it as a time invariant system. Suppose I am taking an input signal xt produces an output yt. So if you are producing x, then output is your yt. Then any time shifted input xt plus delta result in a time shifted output as ty of t. So we are taking an example of these two systems. Suppose one system is yt equal to t of xt and another one is a yt equal to 10 of xt. Now see that which system is autonomous and which is dependent on time. So now if I am taking a system A, now suppose I start with some delay time. So xdt is nothing but x of t plus dt delta. So what is yt? Yt, according to this function, it is t into x dtt. So y1t is t x dtt, which is t of xt plus delta. Now if I am taking a function as a delay function, y22, which is a y of t plus delta. So it gives to you t plus delta of x of t plus delta. Now see the difference of these two functions. So these two are not same. That's why this system is not time invariant. So it is a non-autonomous system. But if you see this system, yt is 10xt. If you are changing it, so then what you are getting? In the y1t, it is 10 of x1t and y22 is also of 10 of x2t. So it is in both the cases is the same way. So that's why this system is a time autonomous system and this system is a time dependent system. So see here it is in this case y1t as well as ytt, you are getting the same. So both the input are same. So you are getting this as a autonomous system. Now we are coming to be the conservative system. In this case, the total mechanical energy remains the constant, and that is the important portion because most of our oscillators or simple pendulums, which are depending on the this type of the oscillations or the where we are considering that energy should remains the constant. So there, this means there is no fluctuation or no oscillations are available in the systems. But when we are coming to the non-conservative system, it is changes and the changes is maybe due to the friction or the damping. So basically conservative systems are the examples of simple harmonic oscillators. But non-conservative, if we are talking about, it is an example of damped harmonic oscillators or pendulum if we are taking a forced pendulum or the perturbed pendulum. Now we are coming to the discrete and continuous system, and all we know that discrete system is described by a difference equation or a set of equation. In case of a single equation, we are also talking about the one-dimensional map, and we denote time by k, and the system is typically specified by the equation. X naught is the initial value, which is x naught. X of k plus 1 is the f of xk. Means basically your all the previous values are able to define the next iteration. So xk, if we are taking, it is nothing but fk times of x naught. So x naught is x naught, means x1 if we are saying, so x1 is f of x naught. Okay, same to x2 is f of x1, like this thing if you are multiplying, so you are getting f is square of, like x2 is nothing, f is square of x naught. So this system can be solved easily by the iterative calculations, and of course that is an important one. And I will show that how we have to find out the iterative system, and these iterations how are making a complex systems as a simple or complicated. So simply, this is an example, like annual progress of a bank account. If the initial deposit is suppose 1 lakh rupees and the annual interest is 3%, then we describe the system as x naught is initial amount, which is a 1 lakh. Xk plus 1, if we are talking, it is nothing, 1.03, because the interest is 3%. So it is 1.03 into xk. So xk is nothing but the function 1.03 to power k, because how many times you are taking, that is giving you the amount. If I am taking after the 2 years, then it comes to be the amount as 1.03 square into the 1 lakh amount. So that gives you the amount which is applicable or which we customer has to pay after the 2 years. Now, if we are talking about the continuous system, it is described by a differential equation or a set of equations. And these equations are normally defined as a differential equations, like x dash equal to fx, which is depending on the initial condition, x naught equal to x, so x of 0 equal to x naught. All the functions what we are taking is depending on the initial values, because we are not getting a solution in a closed form. That's why it is required to find out the initial value. If it is given, then we are able to find out the further iterations or the solutions of the any system. For example, if we are defining the vertical throw based on the initial conditions h naught and v naught, and the equation is like h dash equal to vt and v dash equal to minus of g. So of course h is against the velocity, so it is velocity, and this is against the gravity, that's why you are taking minus of g, where h is the height and v is the velocity of a body. Now suppose I am taking a simple example of these. When the reals are acting, the system is called a continuous dynamical system, and when the integers are acting, then the system is called a discrete dynamical systems. So this is in Mathematica. Basically they gave, if we are dealing with the real numbers, then it is a continuous dynamical system. If we are dealing with the integers, then it is a discrete dynamical, because then you are selecting only the points, not the complete system. One-dimensional map or one-dimensional system, of course, it is depending only on a single function. Suppose if we are saying xk plus 1 is depending on the earlier iteration, which is axk plus v, or we can say x dash t equal to axt plus b, where a and b are constant, so it is depending only on the one variable x. But if we are talking about the multi-dimensional system, so it is denoted as a x bar k plus 1 equal to ax bar k plus b bar, where a and b bar, these are the vectors, position vectors, and x bar is your vector with n components, and it is denoted in a matrix forms. And earlier I think this program we discussed a lot about the linear algebra based on these equations. So a and b are the matrix, and we know that how to find out the multidimensional systems. Now we are coming to the eigenvalues and eigenvectors. Basically, we know that eigenvalues are nothing and eigenvectors. These are applicable for a square matrix. And these are the non-zero vectors, which after being multiplied by the matrix, remain proportional to the original vector. So that is only change in the magnitude, not in the direction. So for each eigenvector, the corresponding eigenvalue is the factor by which the eigenvector changes when multiplied by the matrix. So basically you have a u bar vector is lambda u bar vector, where lambda is the eigenvalue and this eigenvector u bar is the eigenvector. So you see that this is the some vector position, and this gives you that if you are multiplying lambda times, how much is the change in the vector position. So for the eigenvalue calculation, we know all that we are using the formula as determinant of this matrix should be 0, where A is the matrix which is given, lambda E is the identity matrix. So A minus lambda I should be your 0, and which is given as A11 minus lambda, A12, and like this. It is a square matrix whose determinant should be 0. So by solving this as a characteristic equation, you are finding the eigenvalue of the system. So, and the eigenvectors are corresponding to this equation, which is the matrix A minus lambda I, u bar equal to 0. So if we have a two-dimensional example, then we have A11 minus lambda, A12, A21, A22 minus lambda, and U1, U2 equal to 0. So by solving, we are getting a lambda 1 and lambda 2, which are the eigenvalue, and corresponding to these eigenvalue lambda 1 and lambda 2, we are finding the values of U1 and U2, which gives us the solution for lambda 1 and lambda 2. So if we are successful in finding eigenvalues, we can say that we find a diagonal matrix which is similar to the original matrix. And diagonal matrix has the same properties like the original one for the purpose of solving the dynamical system. So we write down the diagonal matrix of this comes to be, suppose eigenvalues are lambda 1 and lambda 2. So we simply got it as a lambda 1 0 in this case, and 0 lambda 2 as a eigenvalue value or the diagonal matrix. If we have n dimensional, then we have lambda 1 and the corresponding 0 0 0 and like this thing. Now we are coming to be a simple matrix. Suppose we have a matrix as 4 2 1 5. Now we have to find out the eigenvalue. The simple is 4 minus lambda 2 1 and 5 minus lambda, and we are solving 4 minus lambda into 5 minus lambda minus of 2 and solving and finding the eigenvalue. Then this is the characteristic equation, and when we are solving it, we are getting this equation, and when we are solving, we are getting the eigenvalue as 6 and 3. So if we have to write down the diagonal matrix, it is nothing but 6 0 and 0 3. Now corresponding to this, we are finding the eigenvectors. So simple is eigenvector calculation. It is 4 minus lambda 1, 2, 1, 5 minus lambda 1 of u1, u2. So 4 minus lambda 1 means if we are taking 6, it comes to be minus 2, 2, 1, minus 1, u1, u2 equal to 0. So you see that both equations are similar. So you are getting only one equation, u1 minus u2 equal to 0. This means u1 is equal to u2 in the case of 6. So you are getting the corresponding eigenvector as 1, 1. Now we are taking the another equation. So it is 4 minus 3 means 1, 2, 1, and 5 minus 3 is 2. So again you are getting the similar equation as u1 equal to minus 2 u2. So if u2 is 1, u1 is minus 2. So you are getting the two eigenvectors corresponding to these eigenvalues, which is 1, 1 and minus 2, 1. And as we discuss in our engineering student and the matrix also, now you are easily able to find out the model matrix by writing the eigenvectors as 1, 1 and minus 2, and then inverse finding diagonal matrix and the other ones. And we have to check whether it is positive definite or indefinite, and accordingly we are finding the solution. But I am not going in that dimension. I am going towards the how using eigenvalues we are finding the stability of the function. So any vector that satisfies the condition u1 equal to u2 is an eigenvector for the lambda equal to 6, and which satisfies this condition is an eigenvector for the condition lambda equal to 3. This is the Mathematica program of this one simple way. Matrix is your 4 2 and 1 5. So if you are writing this, you gives this eigenvalue, simple write down eigenvalues, you get this solution. And eigen system, you are getting this as a eigen system of the value. So first is corresponding to your eigenvalues, and the other one 2 1 is the eigenvectors corresponding. First is corresponding to 6, another one is corresponding to the 3. So in Mathematica, it is very simple to calculate the eigenvalues and eigenvectors of any system. Now we are coming to the what is the trace. Trace of a matrix is the sum of the element on the main diagonal. So it is nothing but the giving you the elements as a sum of the diagonal elements. Jacobian matrix is the matrix of all first order partial derivative of a vector or scaled value function with respect to another vector. The matrix is normally denoted as J or DF or A. So Jacobian, suppose this matrix, this system of equation is given. So what is the value of Jacobian? It is nothing but partial derivative of this function with respect to all the variable. So it is del f1 by del x1, del f1 by del x2, and like del f1 by del xn. Same way del f2 by del x1 and up to so, and like this thing. So this is the Jacobian of a function. Now, if we have to check the stability and fixed point. So a fixed point is a special point of the dynamical system which does not change in time. It is also called an equilibrium, steady state, or singular point of the system. So how we have to find out? Simply whatever be the equation is given, put it equal to 0. So if a system is defined by an equation dx dt, dx by dt equal to fx, then the fixed point can be found by putting fx equal to 0. So when you are changing this, you are getting the dx by dt equal to 0. So you got the equilibrium point or the fixed point of the system. For discrete time, we examine the condition that fx means for continuous, it is dx by dt is 0. And for discrete system, it should be equal to x bar. Now we are coming to be what is the attactor, how we have to find out it. So attactor is a set towards which a dynamical system evolve over time. So as time changes, what is the system behavior? It is calculated through the attactor. It can be a point, a curve, or more complicated structures. Now my main emphasis is in this is how to find out different attactors and how it looks like. A stable fixed point for all starting value x0 near the system converges to this system as t tends to infinity. This means as time tends to infinity, it remains to be a fixed point and all the points are converging towards this point. Then it is known as a stable point. Marginally stable means all values are evolving around this but not converging to this. And unstable is that the system moves far away from this point. Like I am showing this thing. Suppose you have this point. This is a stable point because all the trajectories are coming closer to this point or moving or attracting towards this point. Marginally stable, like this is a point. All the trajectories are revolving around this point, but not merging to this point. And unstable is that this is a point, all the trajectories are moving away from this point. So these are the basic properties based on this fixed point, that what will be the stable, marginally stable, or unstable points of a system. Now we are coming to be the phase portrait or phase space. It is a space in which all possible state of a system are represented, with each possible state of the system corresponding to one unique point in the phase space. It is a two-dimensional system and it is called a phase space, which occurs in classical mechanics for a single particle moving in dimension and where the two particles are position and velocity. So basically what is the phase space? It is the, if in simple manner, if I will explain, it is the graph between the position and velocity, or you can say x and x dot plot is known as a phase plane. So there you are not taking time. This time is there, but it is a silent feature. So you are plotting between x and x dot. The graph or the plane is known as a phase plane. So of course, it usually consists of all position and velocity variables. And the plot is called the phase diagram. It is a plot of single phase curve or multi-phase curves corresponding to the different initial condition in the same phase plane. Like suppose now we are taking two-dimensional system. Let the function is x1 equal to f1 of x1, x2, which is nothing but ax1 plus bx2. x2 is nothing but cx1 plus dx2. Now our system is this one, ax1 plus bx2, cx1 plus dx2. Then based on these condition or variable values, we can find out how the system evolve. Now if we are writing the Jacobian of this system, it is Jacobian is del f1 by del x1, del f1 by del x2, del f2 by del x1, and del f2 by del x2. So if we are taking del f1 by del x1, it is A, B, C, D. And when we are finding the Jacobian, So this is the Jacobian. If we are writing its characteristic equation, it is A minus lambda, B, C, D minus lambda equal to 0. So determinant of this matrix is 0. And when we are solving it, we are getting the equation as lambda square minus sum of these values. So A plus D lambda plus AD minus BC equal to 0. If we solve it, or in simple terms, it is nothing. Lambda square minus A plus D means the sum of the diagonal element, which is nothing but trace of A. So it is lambda square minus trace of A lambda plus AD minus BC is nothing but the determinant. So generally the characteristic equation is denoted as lambda square minus trace A of lambda plus determinant of A equal to 0. And if you are finding its eigenvalues or the roots, lambda 1, 2 is nothing but trace of A plus minus trace under root of trace A square minus 4 times of determinant A by 2. Now if you are solving it, trace of A square, now based on the different condition of this under root, you are getting the different type of the systems. So if trace of A square is greater than 4 determinant A, so you are getting a 2 real and distinct roots. And if trace of A square equal to 4 determinant A, you are getting a 1 system or a coincident root. And if trace A is less than 4 determinant A, then you are getting it as a complex system or the imaginary points. Now how to calculate it for finding the different type of the behavior of the system. Like if we have a system as a x1 dot equal to minus x1, x2 dot equal to minus 4x2. And if we are finding it, and then write down the eigenvalue. And if we are solving the matrix, we are writing delta of delta x1. So delta by delta x1 of this is minus 1, 0, 0, minus 4. And when we are finding it, the eigenvalues of this comes out to be minus 1 and minus 4. And correspondingly, if we are writing that, then we are finding the eigenvectors as corresponding to minus 1 is 1, 0. And 0, 1. And if you see the values of this or the graph of this, you are getting this. And see that all are, because you are getting two distinct roots which are negative roots. That's why you are getting that all the points are coming towards this point. And so you have a behavior as a attracting node or sink. Now if you have another behavior which is so x1 dot is x1 and x2 dot is equal to 4 of x2. In this case, you are getting it as eigenvalues are 1 and 4. So you are getting the both are the positive roots, means positive eigenvalues. So in this case, you are not getting it as a stable fixed point, but the points are moving away from this. So it is an example of a repelling node. This means if you have a negative eigenvalues, then you are getting a stable fixed point or your node is the sink. If you are getting a positive eigenvalues, then it is a repelling node and you are getting a system as a unstable fixed point. Suppose you have one system is negative and another one is a positive, like x1 dot is minus x1, x2 dot equal to 4x2. If you are finding the Jacobian, it is minus 1, 0, 0, 4. And if you are finding the eigenvalue, it is minus 1 and 4. And the eigenvectors are 1, 0 and 0, 1. And now you see that in this case, it is neither repelling nor attracting. So this is an example of a saddle point. So in this case, there is an unstable fixed point, which is known as a saddle point. if you have another example where you have both the trajectories are there, means here only one point is there, only one variable point is here, both the variables are there. So if you have x1 dot equal to x1 plus 2x2, x2 dot is minus 2x1 plus x2, and if you are plotting it, you are getting a matrix as 1, 2, minus 2, 1, and corresponding the eigenvalues are 1 plus 2 iota and 1 minus 2 iota. And in this case, the vectors are minus iota 1 and iota 1. In this case, we are getting it as a spiral. But this spiral is because you are getting a vectors as which has the real part also. That's why you are getting it as a unstable point which is moving away from this point. So this is an unstable fixed point. And if you are taking this as a minus x1 plus 2x2 minus 2x1 minus x2 and finding the eigenvectors, then you are getting again a minus 1 plus 2 iota minus 1 minus 2 iota. And if you are plotting it, you are getting this spiral as a attracting one because you have a negative real part. So basically for the stability, it should be a negative ones. So if you have a negative real part, then always it is showing a stable structure. So this is a stable fixed point which is called as a stable focal point or stable spiral. Now if you have this type of the system, and if you are finding the eigenvalues, since you are getting both the eigenvalues as the imaginary, in this case you are getting it as a center point and all are the marginally stable. Means these are moving towards this point but not converging towards this point. So these are the marginally stable. All are the trajectories are moving along this point. So this is the example of a node or your marginally stable structures. Now, these are the behavior which we discussed, but I am summarizing this as the text is as per the eigenvalues are, if all eigenvalues are negative, then you are getting it as a, if all eigenvalues are negative, then you are getting an equilibrium point. If one value is 0, but all other eigenvalues are negative, then you are getting a periodic limit cycle. If suppose k values are 0, but all other eigenvalues are negative, then you are getting k periodic cycle. Sorry, ये mathematically थोड़ा disturb हो गया है, which comes downward. If suppose you have a one eigenvalue is positive, but still sum is negative, then you are getting a strange chaotic. And suppose you have two values of eigenvalue as positive, but still the sum of all eigenvalues are negative, then you are getting a hyperchaotic systems. So basically the attractors has the different type of behavior depending on their eigenvalues. So always if all the eigenvalues are negative, we are getting a equilibrium system. Now these are the stable stars or different type of the based on this one. Suppose you have a x1 dot equal to minus x1, x2 dot equal to minus 2, and both the eigenvalues are same. In this case, you are getting always the star positions, but these stars are stable because you are getting a negative eigenvalue. But in the same way, if you are getting it as a positive eigenvalue, then it is an unstable star, because positive eigenvalues are giving always the unstable system. Now, if you have a system like this one, and if you are finding its eigenvalue, it comes to be -1, and the solution is this, then you are getting again a node which is a stable node because the points are coming closer to this point. And if you have a positive value, then it is an unstable node. Same, but all the points are moving away from this point. So simple case is if eigenvalues are negative, you are getting the stable system. If eigenvalues are positive, then you are unstable nodes or unstable behavior or structure or dynamical system behavior is there. So these are the different phase portrait. A stable node, if all the eigenvalues are negative. Unstable node, if you have both the eigenvalues as positive. If one eigenvalue is positive and negative, then you have a saddle point behavior. If lambda1 equal to lambda2 is not equal to 0 and real, then in this case your solutions are like this one. And you are getting, if lambda is negative, you are getting a stable star. If lambda is
हेलो
positive, you are getting...
हेलो रश्मि मैम
हाँ
मैम मेरे को एक सवाल बस ऐसे पूछना था कि आप जो ये फेस स्पेस ड्रॉ कर रहे हो मतलब वी ऑल नो द आइडिया व्हेन द आइगन वैल्यूज आर नेगेटिव देन इट्स ऑलवेज स्टेबल सिस्टम्स आर डायनामिकल सिस्टम्स आर स्टेबल बट द इशू जो मुझे अभी डाउट रहता है हमेशा से कि फेस स्पेस में ये जो सॉल्यूशंस हम लोग ड्रॉ करते हैं ये जो आपने पहले एग्जांपल मैं काफी टाइम से कोशिश कर रही थी आपको कनेक्ट करने के लिए बट मेरे को लगता है तो मैं प्रॉब्लम आ रही थी मेरे ऑडियो में तो मैंने अभी यही पूछा कि जो पिछली आपने जितनी भी स्लाइड्स दिखाई उन सबों में जो फेस स्पेस आपने ड्रॉ करा हुआ है उसका कुछ आइडिया दे सकते हो आप कैसे ड्रॉ कर रहे हो आप उनको?
अच्छा, these are nothing but जितने भी फेस स्पेस हैं द वेरिएबल
कोई
इज
सिंपल सा दे दीजिए शुरू में ही कोई भी सिंपल वाला
जैसे यही वाला एग्जांपल सपोज यू टेक एनीवन यू टेक x1 and x2 simple this is nothing x1 dot equal or one equation is x1 dot another one is x2 dot okay
yeah
so this is a plot between x1 and x2 which is varying with time okay
yes
so time we are not plotting but we are taking a different values of x1 and x2 we are plotting so this is a mathematical plot मैंने इसमें से हटा दिए हैं I will share the another slide with you where you have the program of this where you are plotting with this ना
हाँ सिर्फ एक आइडिया कि कैसे प्लॉट हो रहे हैं आप मैथमेटिका में कर रहे हो या मैटलैब में कर रहे हो?
ये मैथमेटिका में है
ओके मैम तो अगर आप एट द एंड ऑफ द
मैं अभी एंड में हो सकता है इसमें रखी भी हो कोई स्लाइड I will show you that how we are doing that ना
okay
so basically it is clearly showing you हो सकता है इसमें लास्ट में हो I will show you that
okay.
I will take care of that okay
ma'am thank you
and same way miss if lambda is negative you are getting a stable structure positive you are getting unstable and same way if you are getting a different type of the structure where both eigenvalues are 0 then we are getting equilibrium subspaces. Same way you have when eigenvalues are having the both the means it is a complex numbers and if you have a alpha as a positive one then we have a different structure. If it is negative then always you have got a stable focus. If alpha is positive you are getting a unstable focus and if alpha is 0 then you are getting a center. Already I showed all these examples but I categorized specifically. Now this is the complete system where you get all the ideas. Basically your determinant is p square minus 4q. It should be positive here, it is negative here, and on this curve it is 0. So this is the basically your trace of a or p. This is determinant of a or q. If a point is on this q line, you're getting a stable center. If it is on the determinant is negative, you are getting either stable spiral or unstable spiral or stable node or unstable node. If it is on the equal to 0, you are always got the nodes as a stable or unstable. If it is in a positive determinant, then always you are getting a unstable saddle points. And this example already I have taken in detail. So you just this one slide will give you the complete structure how we are finding the different type of the phase space or trace or determinants. Now I am coming to the mathematical modeling processes where we are using the different type of the nonlinear tools. Basically, if any problem is given, our main purpose is to that the real world problem we simplify as a working model. Then we represent that model as a mathematical model based on some different conditions or variables. We try to construct a mathematical model. Then we translate this mathematical model into the computational model, as asked by Jyoti also, the how to find out the solution of this one. And then we simulate and finding the results and conclusion. And these result and conclusion we interpret in terms of the real world problem again. So in simple, if we say this is the complete our system, any real world phenomena is known as a real world problem. Now we determine this real world problem using our mathematical interpretation into a mathematical language. So there are the normally the three ways of solving this type of the language. Either we have a through data systems, so data analysis, or we define the continuous equations, or we define the discrete systems. So basically either it is a data points, or it is a continuous ones, or it is a discrete systems. So either we collect the data or develop continuous equation, or we define discrete characteristics. Using all these, we whatever be the system we take, our purpose is to design the model using the governing parameters. Means whatever parameters, suppose I am taking a weather analysis. So we have the different type of the data, like temperature is there, humidity is there, wind speed is there, then the precipitation is there. So different type of the parameters are there. So we have to design those. Nowadays, during the COVID or the epidemiological modeling, you are taking the different type of the parameters. So using those parameters, we are using or designing the governing equation or parameters. With this, we try to find out either the analytical or numerical or asymptotic solutions. With these solutions, we try to analyze the solution and predict the future possibilities. Then we try to validate these data, which are based on the different parameter. Then we are implementing the result and again interpret in terms of the real world problem. So this is the simple flow chart of this problem. We start any problem, formulate that problem, and now this problem is either basically based on the mathematical parameters. So your problem is either a continuous or discrete or the parameter or the data based. We try to find out the solution. We find out the evaluation. If we are satisfied, we stop it. If we are not satisfied, again we are finding the same way of changing the parameter. So this is a simple flow chart which we are using normally in the computation of a real world problem. Now we are coming and showing you the simple structures, that how you are getting a complicated structures. It is simply based on the iteration process. Suppose this is a plus sign. Now on each plus sign, means on each line, you just again draw a plus sign like this thing. Then again you draw. Now you see in the 3 iteration how complicated structure you are getting it. But the beauty of this structure is if you are taking a small part of that, and if you are zoom in, you are getting the again the original structure. So this is the beauty. We are using iteration functions. We are creating the complex structures, and these complex structures are basically iteration of the initial structure. So by zooming in, we are having these properties. So if we take a small part for any complex system, if we are getting a resemblance with the original system, we try to correlate the relation between these two systems. So this type of you see that how in a simple way the complexity grows. So in our body, in our lungs, we have this complexity. All our spiral structures has this type of the complex structures. Simple example, in our daily life, we have a broccoli or the cabbage or cauliflower. If you have a cauliflower and see or broccoli, if you take any part of that and if you zoom in, you are getting similar structure. So this is the beauty, and if you are able to transform or to find out some properties related to a smaller structure, similarly we can able to find out for the bigger structure. So this mathematically is known as a fractal, and this term is coined basically in 1975, and it is an extremely irregular line or surface formed of an infinite number of similarly irregular sections. Physically, it is a rough or fragmented geometric shape that can be subdivided in parts, each of which is a reduced or size copy of the whole. But mathematically, if anyone asks that what is the difference in these structures and the earlier one, basically these structures you cannot define through the Euclidean geometry, because these are the curves which are not coming into the Euclidean geometry. So fractal dimension or fractals, mathematically, it is a set of points whose dimension exceeds its topological dimension. Basically, topological dimension, we know that for point we have a 0, for line we have a 1. Same way we have a curve or the two-dimensional curve, so 2. Similar way, but here we don't have a 0, 1 or 2. It is maybe a fraction parts. So fractal dimension, it is a statistical quantity that gives an indication of how completely a fractal appears to fill space as one zooms down to inner and finer scale, and normally it is denoted as a 2 minus h. It is also denoted as Hausdorff dimension based, which is nothing but log of n epsilon by log epsilon, limit epsilon tends to 0, where this n epsilon is the number of open balls of a radius epsilon needed to cover the entire set, and such that we are plotting these open balls such that the d of px is less than epsilon. So you are taking a small open balls which are covering the complete space, and then if we are getting a dh as minus limit of this, if it is coming to be a value, then we say that it has a fractal dimension. Now it is very simple because it is generated through the iterations, and if anyone interested, we can discuss later on. These are generated by iteration of an algorithm or formula. I'm taking a simple example, Koch curve. What we are taking, we begin with a line, divide this line into 3 parts, remove the middle part, and instead of that, join it with the 2 lines. So you are getting this structure. Now this is the one iteration, complete one. So what you are doing, you divide a line into 3 parts, remove the middle part, and join with 2 lines. Now same structure we are repeating again. So this is a line, divide it into 3 parts, remove middle part, and join same way in the. So the second iteration is your this one. Same you repeat. This is your third iteration. Now see that how complicated structure you are getting it. And so this, if anyone asks that what is its dimension, how to find out that? So it is nothing but easy way of finding it is the log of the number of new pieces divided of the log of the number of the initial pieces. New pieces is 1, 2, 3, and 4, and the original pieces is 1, 1, 2, and 3. So it is log 4 by log 3, and it comes out to be 1.26. Now you see that it is not an integer value, and as neither it is a one dimension line nor it is a complete triangle, that's why its dimension is neither 1 nor 2, but it comes to be in between of that, which is 1.26. And this is the most I can say an important one, Sierpinski triangle, because now in everywhere we are using this Sierpinski triangle, and it is very helpful because nowadays we are using a fractal antenna in our communication systems, and this fractal antenna is nothing but based on this Sierpinski triangle. What we have to do, we join the middle part of the middle point of the triangle lines and remove that part. So when you are removing it, now remains the 3 triangles. Again join this and do that. So this means initial structure is 1 and you are getting 1 piece. Then you divide the point in the half part. So you have the 3 structures. Now you are dividing into the 1/4 part, and their structure is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So like this thing. And if we are finding its dimension, it comes to be 1.585. Again, because it is not remains to be the triangle itself. So that's why the dimension comes to be 1.585. And see that how much iterations are possible. And if you have to check this type of the triangle, you get all variety of the triangles here. So it is self-similar, exactly the same structure repeated all over the fractals. If you zoom in any part, you are getting this thing. So it is immaterial of the rescaling also. So there is no typical size of object, length, scale, and it contains all possible size, and there is a practical limitation, of course, depend on the computer, how much iteration or resolution is possible. How we have to generate it? It is easily generated with the iterated function. What is the iteration function? Suppose start with the function x square plus constant, and constant is a seed or x naught. Now, as I said that your all the function are x naught. X1 is nothing but f of x naught. So what is x1? X naught square plus constant. What is x2? X1 square plus constant, like this thing. Now our purpose is to find out what is the behavior or orbit. So we have to find out the orbit of x naught or where it should move. And in a simple manner, I will show that how it is changing. Suppose I am taking a simple example, x square plus 1, and start with the 0 value. So what is x naught? 0. X1 is 1. X2 is 2. X3 is 5. X4 is 26. And when you are putting 26 square, so it comes to be 677. And when you are putting 677, it comes to be 4,58,330 value. So this means if anyone asks what should be its behavior, of course it tends to infinity. So James Clerk said that in the mind's eye, fractal is a way of seeing infinity, because in general you can't say, but through this you can visualize that how much iterated functions or values are giving you the value of this function. Same way, if we are starting with x square plus 0, you got it as a 0, again 0, 0, 0. So it is moving towards a fixed point. If you have x square minus 1, then 0, minus 1, 0, minus 1, like this thing. So you are getting two cycles. Some points are converging towards the 0 and some towards the minus 1. So like this type, you are moving to the 2 cycle. If you have z square plus iota, starting with C0, see the beauty of this. So what you have, you started with 0. So the value is 0, point is 0, 0. If you are substituting 0, then in the first iteration, you are getting iota, which is nothing but 0 and 1. So this is the point. When you are putting iota, you are getting minus 1 plus iota. So it is the point minus 1 iota. And when you are putting minus 1 plus iota, you are getting minus iota. Now you see that all iterations are moving towards only these 2 points. So it is again a 2 cycle. And the beauty of this thing is in human anatomy, we are using the application of fractals, and it is very useful. Our bronchial tubes have a fractal dimension, which is very close to 3. Our arteries has 2.7. Our brain has 2.73 to 2.79. Our alveolar membrane has 2.17. And now the research is going on to find out this chromatin material. It is a fibrous material inside the cell's nucleus, which contains the genetic material, forms the cluster, which has the fractal dimension. And now the research is going on to find out that to detect the breast cancer based on this fractal dimension of chromatin. And the Bhabha Atomic Research Center, Indian Medical Association, in Mass and DRDO is working in this. And I am also a part of this team. So we are very close and hope so in future we are able to find out its fractal dimension. This is the fractal canopy of the approximation of a lung. And during the COVID, you see that the most affected part is the lungs. And the reason is that because it has a fractal approximations. So if any part is affected, it is spreading very fastly. Same way, if you have our neuron, these also has the fractal property. And this is the reason that within a fraction of second, the signal transfer from brain to any part of the body. Now we come to the bifurcation of that. I'm not going in detail about the bifurcation here. In the next lecture, I will take that. Only I'm giving the glimpses of that bifurcation. Basically, it was firstly introduced by Henry Poincaré and in 1885. And he showed that that there are the different types of the stationary points. And then it was named as a Poincaré sections are also named after that, and bifurcation also. He said that bifurcation occurs when a small smooth change made to the parameter values of a systems causes a sudden qualitative or topological change in its behavior. It occurs in both continuous system and discrete systems. It is the mathematical study of changes in the qualitative or topological structures of a given family, such as integral curves of a family of vector field and the solution of a family of differential equations. It is useful to divide bifurcation in two principal classes. One is a local bifurcation, which can be analyzed entirely through changes in the local stability properties of equilibria or periodic orbits or other invariant systems, and global bifurcation, which often occurs when larger invariant set of the system collide with each other or with the equilibria of the system, and that cannot be detected purely by stability analysis of the equilibria or using fixed point. So now I'm taking a very simple example and showing that how it is bifurcating. Suppose you take a simple logistic growth model, which is xn plus 1 equal to rxn minus r of xn square. So of course it is a iteration process. R is the fixed parameter, which has the value fixed. And as you are changing x naught or xn values, you are getting a different type of the trajectory. Now suppose I start with the initial value r as x naught, sorry, r as 0.5 and x0 as 0.5. So you see that after some iteration, this type of the behavior is going towards the zero. So if we are taking this as a population model, so after some time, this type of the population become extinct. If I'm taking r equal to 0.8 with the initial value 0.5, then again you see that after some more time, but this also goes to be extinct. Same way, if you are taking r equal to 1.0, then again it take much more time, but going to be extinct. But if you are coming to r equal to 1.5, then this type of the population is coming to be as a stable one, which is 0.33. So it is moving towards with this stable fixed point. Same r equal to 1.5, only change is that initial value changed, but again you are getting a 0.33 value. If you are having r equal to 2.5, then again it is a stable one with 0.6, but see the change. As you are coming, r is 3.2. So the initial value is 3.2. You see there are the 2 points. So either it is moving towards the 0.79 or 0.51. So this means from r equal to 3.2, it is bifurcating to two parts. Some are going towards the 0.79, some are going towards the 0.51. Now, if you are moving r equal to 3.5, it is going to be the 4 points. Same if it is r equal to 3.55, it is going to the 8 points. So it is going bifurcating continuously. And this is the curve, if you see that. And this is the curve which is bifurcating into 2, 2 to 4, 4 to 8, and like this thing. In the tuber growth cells, this is the structure which is happening. And for chemotherapy session, if suppose any chemotherapy session is done here, this means this complete cell goes out. But if it is done here, then this goes, but this remains. Same way, if it is done here, then only this structure goes, but this complete growth is there. So it is very important that at which node or at which cell that this chemotherapy session has to be done to and see that in a small space of time, how complex structure you are getting it. Now, this is the structure which you are getting in case of the bifurcation or in case of the lungs structure, and see that how soon you are getting a complex structures. So our fractals are in, our lungs are fractal in nature. Kidney also has the fractal behavior. All these are already I showed that in the lungs, in the bronchitis, means all have the bifurcation in the this fractal structures. In our this retina analysis, this is the very beautiful quote by the Hammersmith in 1989. If you like fractals, it is because you are made of them. If you can't stand fractals, it's because you can't stand to yourself. And that is true also, because our body is completely a fractal in nature. And if we are able to predict that or able to find out the particular disease at a particular time, then we are easily able to cure it. Otherwise, it is showing a complex nature. Now we are coming to the time series analysis. So this is a one tool for finding the nonlinear structures. It is a comprising method for analyzing time series data in order to extract meaningful statistic and other characteristic of the data. It is a series of data points in time order. So it is taken a sequence taken at a successively equally spaced points in time. These are very frequently plotted via line charts. And now I'm not taking about much values about the time series. I'm taking a simple example of this. This is a continuous system. Dx by dt equal to ax plus by, and dy by dt equal to dx plus cy. This is the system. Here, as you are changing, and this is the graph. If you see that it is a graph between x, means the time, and x value, time and the y value, and this is the plot between xy time series. So if you see that as you are taking a value as -6, b value as -8, c value as 5, and d value as 6, you are getting this structure of the series. First series, this I think it is visible. Blue series is your x series and green series is the y series. You see that there is the fluctuations, but after some time it is coming to be the regular as a 0, 1, both the series. So it is a regular structure. But if you are taking a equal to -6, b equal to -8, c equal to 6, and d equal to c, so you see that both the trajectory blue and green both are moving as a around that, but not moving towards that. So it is a marginal, stable, or you can say intermittence case. But here, if you see a equal to -3, b equal to -20, c equal to 3, d equal to 9, you are getting a behavior which is not following any pattern. So it is a chaotic behavior. You see that the time changes in all the three cases only depends on the parameter A, B, C, D. As you are changing the parameters, then you are getting a different values of the different time series. And you see the time is also varying in all the cases. Phase space, as already asked, that it is a plot between x and x dot. So here also we take the similar example. It is a phase plot between x and y. This is also x and y, and this is also x and y. Here also we take the earlier same variables. Through phase space also we plot, see that it is coming closer to this point. So this is a regular case. Here you are moving around that point, but it is a marginally stable case. In this case, it is very difficult because this portion is wider and you are not able to find out the point where which point is. So it is towards a chaotic or a unstable case we are getting it. Stability analysis, one way is already we know that through the Jacobian we have done. And the point is called an equilibrium point if we are putting du by dt equal to fu. So if fu equal to 0, you are getting a points. So if we have a three-dimensional system, Jacobian already we know partial derivative of this fx, fy, fz, gx, gy, gz, hx, hy, hz at an initial point x naught, y naught, z naught. If all eigenvalue have negative real part, as already I showed you, then it is asymptotically stable. If some eigenvalue of j have positive real part, then it is an unstable part. And this is the important test which we used in studying the stability test, which is a Rouse-Hurwitz stability test. What we are doing, this is the equation which you are getting through the Jacobian as a eigenstructure. Lambda cube plus b1 lambda square plus b2 lambda plus b3 equal to 0. If we are finding the fixed point using this thing, and if b1 is greater than 0, b3 is greater than 0, b1 b3 minus b2 is b1 b2 minus b3 is greater than 0, then you are getting, if all these three conditions are satisfied, then it is a stable fixed point, but the root should be a negative real part only. Then only this is a stable fixed point. As already I told that there are the different models: empirical model, theoretical model. Empirical model are based on experiment and observation. Theoretical models are based on statistical, mathematical, and computational way. Now I'm taking at this three-dimension system, and this is nothing in journal. If you know that it is a Lorentz system, dx by dt is ay plus bx, dy by dt is rx plus my plus cxz, dz by dt equal to kxy plus bz. If you see this system, okay, and as I am varying the different parameters, I am getting a different structures. You see here this one. So there are the different phases of dynamics: stable spiral, limit cycle, chaos. For stable spiral, you are getting a structure as this structure, and this is also a phase space in the three dimension xyz. If you are taking any section of this, you are getting a stable structures. Same way for y dimension, xy, xz, yz, and if you are, these are the time series, so you see that you are getting a stable structures after some time. All these are, and this is the RQA analysis or time series analysis. As you see that as time varies, initially it perturbed, but after some time it is a regular structures. So this is showing a regular behavior of the time series. All the three are the regular structures. But if it is a limit cycle, you see that if you are structuring it, it is revolving about that, but it is a marginally stable. Means this is a intermittence state where you are getting all as a limit cycles. Same in xz. And this is the phase space analysis where x1 and x2, if you see that here what we are getting, these are all are repelling outside. All are the repelling curves. Here you are saying this is the point and this is the attractor. All curves are moving towards this point. So this is the case of the attractor behavior. And this is the catastrophe or the attractor, which is showing that it is the extinct. I have shown in the first slide. So this is the point. All are showing that it is a catastrophe or extinct position. These are the time series which we have shown earlier, that as time varies, one trajectory is going this way and another one is this showing the repellent behavior. So if any time after some time you're not able to find out the both trajectory and the same lines, these are moving parallelly. Here both are merging together. So these are the simple example as a catastrophe which I already showed you. This is the XYZ axis. And you see that here, after some time, these are showing a periodic behavior, means it is showing not a regular one, but intermittence state. And you see that this is also moving like this thing. So you have a different type of the structure like these ones. But if you have a chaotic structure like this behavior, here you are not able to point out which trajectory is which one. So this is XY species, XZ, YZ. And this is the example which I have taken in the earlier slides, that if you have a Duffing oscillator or Duffing equation, this equation is a simple x double dot plus kx dot plus x cube minus x equal to q of cos omega t. It can be transformed into the three-dimensional system by taking x dot equal to y. So when you are taking x dot equal to y, this equation is y dot plus ky, this remains as it is, plus x cube minus x equal to q cos theta, where theta dot equal to omega. So here we transform this into the three-dimensional system using this equations. And as we are plotting these ones, so here you have this q. If this q is 0, this means it has a simple structure, because this is nothing but this force is not there, so it is a perturbed pendulum only. So when q equal to system, we have the 3 points, minus 1, 0, 1, 0, and 0, 0, where these are the different type of the periodic cycle. I'm showing you. When q equal to 0.2, there is a period 1 harmonic solution. When q equal to 0.28, you have a period 2 cycle. I will show in the graph. Here you see. If q is 0.2, here you have a simple curve which is showing only one period. When q is 0.28, here you have two structures. One is this cycle, another is this cycle. And see that you are having these two cycles. This is a phase space x and x dot. This is a time versus position curve. When you have a q equal to 0.29, again you have two structures. Here the two limit cycles you got. When t is 0.37, now you are getting a different type of the structures. So you see, one is this trajectory, 2, 3, 4, 5. So according to the different structures we are getting, means one up is there, one is there, 3, 4, and the 5. So total is 1, 2, 3, 4, and 5. So you have the 4 points here. This is a when 0.5, you are not able to check that which one is. So see that it is a chaotic curve. Same again, it is again transformed to the two periodic. This is a Duffing equation bifurcation diagram, as this curve divided into 2, 2 to 4, 4 to, and like this thing. These are the different trajectory. All these plots are plotted in a MATLAB program, simple program. And now I think, should I take, or I will show the that.
Yes, ma'am, you please continue.
This is the application which we applied in the COVID-19, where we have applied all this, whatever we take the nonlinear techniques, we applied here to detect the behavior of the COVID-19. All we know that how it is spread and how is the structure of this. So I'm not going in much detail about the COVID-19 structure. I'm coming to the directly that whatever tools I have used, how we have shown here. So basically in any model development, we use the different type of the assumptions when we are doing the epidemiological modeling. These assumptions are common for all the epidemiological models. Basically, it is assumed that the disease is transmitted by contact, direct or indirect, between an infected individual and a susceptible individual. There is no latent period for the disease. That is, the disease is transmitted instantaneously when the contact takes place. All susceptible individuals are equally susceptible, and all infected ones are equally infectious. Population size is large enough to take care of the growth of the model. So if we are taking this, we are considering, of course, a closed structure or a fixed size of a population. Basically, SARS-CoV we have calculated with the different models, follows the fractal behaviors, and it has a fractal geometry. And I will show you that how it has a different type of the. And before going to any structure or any analysis of this, basically all the epidemiological modeling is depending on the basic reproduction ratio. And as this reproduction ratio is becoming larger, then there is this epidemiological, it becomes the pandemic. So it is the average number of secondary cases arising from an average primary number cases in an entirely susceptible population, or the rate at which new infections were produced by an infectious individual in an entirely susceptible population. So basically it measures the maximum reproductive potential for any infectious disease. And it is normally denoted by R0, which is depend on disease and host population. And if it is greater than 1, so it is always considered that it is transmitted to more than one host. I'm showing you the, let R0 is 2. So what is initial phase? Means one is this is an infectious person. Because R0 is 2, this means this person is going to infect to the, if he or she comes in contact with the other person, so that disease is transmitted to the two other person. So in the first iteration, it is transformed to the two persons. Now, because this is R0 is 2, so this person again goes to infect the two other person. So see that how this bifurcation is going on, and in a short span of time, one person goes to infect 2%, 2 to 4, and 4 to, like this, how this is spreading. But if it is R0 is 1.5, this means one person is going to infect in the first stage only to one person. But that one person is in the second iteration is going to infect to the 2%. This means after two iteration, this one person is going to infect the 3 persons. So in this case, it is spreading, but lesser density as compared to the R0 equal to 2. But now because the vaccination is there, so most people are immune. And if R0 is 2, and the infectious person is coming to in contact with the immune persons, so it is not going to infect those persons, because this person is going to only infect a one person, because all other are the immune ones. Same way, this infected person is coming in contact with the immune person, so it is not going to spread the disease. So that's why vaccination is having its impact, because that is not going or stopping for the further spreading of the disease. So basic goal, if we are checking it, like here we are taking the population, which we are considering for the disease, it is denoted as N. Susceptible class is denoted by S. Infected class is denoted by I. And the removed one is denoted by R. And the total population is nothing but the sum of all these three. It is known as SIR model. And this model is initially initiated or defined or studied in 1927 by Carmack and McInnes. And they showed that the total population of any epidemiological model is nothing but susceptible, infected, or the recovered ones. So if we are finding this already I showed you, the Hurst exponent, actually we are calculating this value, which is between 0 to 1. So now if we have used the data, basically the number of confirmed cases which we used for 22nd June to June 2020 in the first phase, which is 160 days. And at that time, Hurst exponent comes to be the 0.81. And it is the case of China, which shows the persistent behavior, because Hurst exponent values is normally lies between 0 to 1. If it is 0 to 0.5, then its value is persistent, anti-persistent. This means it is difficult to predict. If it is 0.5 exactly, then it is a Brownian. And if it is more than 0.5 to 1, then it is a stable structure. and fractal dimension is nothing but 2 minus h. So here you are getting 1.19. As it is less than 1.5, so it is a stable structures. So in long range in the China, it is not infected, neither the confirmed cases nor the death cases or nor the recovered cases. All comes to be the stable structures. But in case of India, it is not true because it is in long-term memory. It shows a fluctuation behavior, which I'm showing here. For that, we have developed a mathematical model. And you see that we take the two type of model. Firstly, we developed. Firstly, we take only three type of the cases, x1, x2, x3 as a susceptible, asymptotically and symptomatically infected ones, and the third one is the removed or recovered peoples. So this means x1, x2, x3, three types of the variables we have taken, and based on that we have developed the model which is given here, where x1 dot is rate of change of susceptible, x2 dot is rate of change of infected, x3 is rate of change of removed one, MB dot, this is the birth rate of the people, means birth rate here means the people, means the who are going to be infected. MD dot is the death rate of the people, which is showing the removal of that. TR is the transmission rate from X1 to X2. Delta P is the proportion of infection rate of people. 1 by omega P is the incubation period, means which is showing you that when it is the we are using in journal the 14 days. 1 by gamma P is the infection period of the people, and this is the lifetime of the virus. Now using this, we have studied the different structures, and here we have used this one, and you see that here we have used for the 60 days, and these are the values of susceptible, infected, and the removed ones. Of course, removed ones we are not discussing much, but you see initially they are the susceptible, but after a 14 days, they are coming to be the recovered ones, means these are the stable ones. So incubation period or that quarantine period of 14 day also justified here in a mathematical form, which I'm showing you in a structure of, these are the time series. So see that initially it is fluctuating, but after some time it is showing a regular behavior. Same way here, but in case of the removed ones, it is showing, of course, the death rate here, but it is again a stable structure. And these are the time series of all these ones. So susceptible and infected are remain in this range, but the recovered ones are going to be higher ones. And but this map we are using for because it is not giving a clear picture, so we comes to be the higher consumption model, and this is the model where we have used the 6 type of the parameter instead of the 3 ones, where we are taking the susceptible are come closer to the exposed one. These exposed one are either the symptomatically infected or asymptotically infected, and both of these are either giving to be the recovered one, or these are the reservoir. Reservoir means, of course, some death cases we are taking it. These are the rate of changes which we are taking corresponding to the every case. So M1X, this is the how transmission rate from the susceptible to the exposed one. MDY from exposed to the different one. So for asymptotically, it is this rate. For symptomatically, this rate. From here, if it is going to the healed or recovered one, it is this rate. And for asymptotically, this rate. And if we are taking the reservoir, so this is the reservoir from these 2 dimensions. And this is a complete structure. And based on this, we have developed this model. This is already published paper. And here, these are the different rates and the different type of the structures which we have used. And based on this, when we are finding it, you see here, I have talked about the eigenvalues. Here, this is a susceptible, exposed, asymptotically infected, symptomatically infected, removed ones, and bias in the reservoir. C in the initial stage. This shows the negative values. This means, and as we know, all the eigenvalues are negative, so it is a stable structure. But if it continues more than the 12 days, then here up to, you see that up to 386 days, it is showing a unstable behavior because we are getting a positive eigenvalues. Okay. But if it comes to be 386 days onward, then again it is coming to be the stable structure. So your quarantine period of 14 days is clearly justified from here. And from 14 days onward, of course, it is giving a complex structure in the body, and then it is recovered after a period of at least 1 year. And these are all the structures, and easily you can visualize here also. It is showing that a graph after a coming of around 100 days, it is showing, but all are moving towards the zero after a period of 450 days. All these are showing that it is coming to be the stable structure. All are coming towards the around a 450 days, and that we predicted in the month of March 2020. May 2020. And based on that, we predicted that roughly the second wave will goes up to May 2021. And it is roughly a period which is June 2021. So we have calculated, all these are showing the phase diagrams. This is showing a period doubling phenomena. If a person is come in contact, again is coming. So it is making a loop systems. All these are the structure based on this one. And this is the complete one. Here also you see that after 13 days, again the values are going on increasing, which clearly shows that the quarantine period is of up to 13 days because it is under control of that one. Clearly all these pictures, and this is the complete structures. If anyone interested, you can go through with the paper. And this is the paper which is published in Chaos, Soliton and Fractals. This is the, I will show in this Chaos, Soliton and Fractal paper, we have taken the data. And what we did, we take the 3 days data to analyze the 4-day data. And then we are using the machine learning and the fuzzification and the wavelet techniques to analyze it. And we got a very good results. And you see that when we are taking a daily cases, this blue one is the exact value, actual value, which comes to be 41. But in our case, which we forecasted, is comes to be 42. So it is very near to that case. And this is the very good model, which has been published in the 2 parts. One is a paper in the journal and one is a book chapter. And this is the model which we developed. It is basically with my co-author from Bhabha Atomic Research Center. This arm is the Rashmi, and D is the Professor Datta from that Bhabha Atomic Research Center. And we modeled this as a RD COVID model. And this is the first kind of model where we have used the data as well as a continuous model. Means all the models we combine to find out the complete structure. Here, firstly, we have taken the data-driven model, transformed it into the SIR model. Then from that, susceptible, exposed, infected and recovered model. And from that, we developed this model, which is a complete model: susceptible, exposed, infected, quarantined, recovered, death, and the protected. So it is basically a SCIQ RPD model. And here you see that because the variables are 1, 2, 3, 4, 5, 6, 7. So we have used the 7 variable. And for that, we have defined this structure. And for solving it means that these 7 equations are depending on the 26 pages calculation. And those calculation we have done, and through which we have analyzed all these things. This we have done in the month of May 2020, and see that through that which we are calculating the result. In the month of May, we have detected that the first wave will be ending in the month of June, and that pandemic will end in the month of October 2020. Then, at that time, we predicted that if the same rate or same thing is there, the basic reproduction rate of the China is very high. It is 2.49. India is very low. It is 1.16. But in case of the China, the herd immunity threshold is 99, but in India case, it is 99.97. So this is the change which is, and here we calculated the total period of China epidemic is only 92 days. India comes to be 461 days. Brazil and Russia comes to be 388 days. And in case of China, it starts from 22nd January 2020, and the end of epidemic is declared as April 2020. In the month of May 2020, we declared that in India, it is roughly approximated date for it will be on May of 2021, which comes to be June in the month. So we are very close at that time. And this is the complete model in the epidemiology, which has the all combined structures, which is known as a Siddhartha model. Susceptible, infected, diagnosed, healed. Then from healed, you have a symptomatically infected and asymptotically or recognized ones, then the threshold or threatened one, or the extinct. And this is the complete model, which is considered as a complete one and which required a lot of calculations. Now we are working on the vaccination model, which is a RD2 model. And through that, we are able to find out that how much it is affected if we are using the model of the vaccination. These are the different type of the machine learning which we can use in the case if anyone is interested. And clearly it shows the quarantine period that this is the kernel vector basically in the support vector if we are using. This is the infected people and these are the healthy people. So it can segregate your quarantine plane, or I can say quarantine to yourself is segregating you from the infected and healthier persons. So mathematically also you can plot it. This is also a linear support vector. This is the infected person. If you quarantine these persons, so of course the other person, healthy people can work easily. So these are the different X-ray models which we are also has a collaboration with the Russia and Italy. So they have provided us the different type of the X-ray structures of the persons who got very much infected during the COVID-19. Through that image analysis, we have to find out what is the major reason of structure of these lungs to find out that what should be the dimension of the fractal and how it was explored in those cases. So these are the some bibliography which we have used here. And these are the some papers which has been published here through using these ones. Now, as you Lakshmi asked me a question. Now, anyone asked me the question, I will show you that program. Anyone can ask that. I am taking if I have some slides on that one.
So any queries from the participant sides? You may please ask.
Is it visible, Lakshmi?
Yes, ma'am. It's perfectly fine.
To see, this is the program in a MATLAB. which we use to find out that curves. You said, you asked that. This is the basically a perturbed pendulum, or you can say dumped acceleration. Here we have transformed it into these two equations. Okay, and these are the initial condition. So we define function dy as a oscillating delta. Okay, t span we have taken 0 to 7, and initial values of this is 1 and 0, these ones. Okay, omega value we have taken as 10, and we use the equation OD45 using this, and we have the plot of y1 and y2, y1 and y2. Clear? So y1 is y and y2 is y dot. So this is a plot between y and y dot. Okay.
Yes, ma'am.
So this is the plot of this which we have used to find out the that phase space. I think this is your question. Hello.
I hope, ma'am, now the doubt is clear, as now the program is clearly visible on the screen.
I will show tomorrow. I will share. This is the Mathematica program of that.
Okay, ma'am. Thank you. So
There you have the x1 and x2 graph plot of that.
Okay, ma'am.
Because I said I have that one, but not put in this slide. All these are the plots which I showed you. All these plots are here. All these programs are here.
Okay, ma'am. So any query from the participant side regarding this session? So thank you very much, ma'am, for sharing your profound knowledge and expertise with all the participants. I hope all the participants really gained a deep insight about the mathematical modeling, that how the disease can be modeled with the help of the differential equations. Because we know that once the differential equation is obtained, then we can solve it, and we will be in the situation, or we will be in the condition to solve and then to elaborate all the phenomenon which is concerned with this, or elaborate the disease process. So I hope all the participants have really explored the session content in a detailed manner, and we are thankful to you, ma'am, once again.
Thank you very much.
Thank
giving,
you.
Thank you.
And moreover, I am thankful to all the participants of this session, and faculty members of Department of Mathematics, and Professor Alka Tripathi ma'am, Head Department of Mathematics. So tomorrow again, we will connect with the same link at 3 p.m. and Professor Rashmi ma'am will continue with their lecture. So thanks to all.
Thank you.
Thank you, ma'am.
Thank you.